All right, so we are working on section 6-4 today. And so as the label says, or the title says, we're talking about the properties of rhombuses, rectangles, and squares. All right. So, parallelograms have specific properties. Well, these shapes are going to have specific properties for the diagonals of our special types of parallelograms. That's where a lot of these properties come from. They're talking about the diagonals in these guys. So first off, the first property for each one of these is the definition itself. That's what makes it the shape it is. Each one of these guys are parallelograms. So all definitions and properties about a parallelogram hold true for a rhombus, a square, or a rectangle. But a rhombus is a special type of parallelogram that has 4 congruent sides. Okay, and of course off to the right side there they have just a generic diagram for what a rhombus would look like. Does every rhombus look exactly like that? No. That's just a generic diagram. Okay, a rectangle is a special type of parallelogram that has, now they say, 4 right angles. Which is true, absolutely true. But please remember that it could also just simply have 4 congruent angles. And the reason I'm telling you that is because it's possible that they don't give you right angles and expect you to know it's a rectangle. It's possible that they give you just a quadrilateral with 4 congruent angles and then expect you to know that it's a rectangle. Okay? So please make sure you know that, yes, it has 4 right angles, but remember that those angles are then congruent. And so if you have a quadrilateral with 4 congruent angles, then you know, oh yeah, we're talking about a rectangle. Okay? And lastly is a square. And a square is a special type of parallelogram that has 4 congruent sides and 4 congruent angles. Okay, 4 congruent sides and 4 congruent angles. So you can say, okay, a square is both equilateral and equiangular, which means that a square is a regular quadrilateral. Remember that vocab word for regular. A regular polygon is a shape that is both equilateral, meaning all sides are congruent, and equiangular, meaning all interior angles are congruent. Okay? So there are the definitions for rhombus, rectangle, and square. So if we look down the page here, we have 2 theorems. Theorem 6-13 and Theorem 6-15, or 14, excuse me. These both deal with rhombuses. So 6-13 says that if a parallelogram is a rhombus, meaning it has all 4 congruent sides, then its diagonals are perpendicular. Okay? If it's a rhombus, then its diagonals are perpendicular. Theorem 6-14. If a parallelogram is a rhombus, then its diagonals are going to be angled bisectors. Now, looking at that fact, and you guys can flip back to your flow chart at the back side of your notes, but we know that a rhombus is also what type of shape? Looking at your flow chart, a rhombus is also a parallelogram. And what do we know about the opposite angles in a parallelogram? They're congruent. So not only is angle 1 going to be congruent to angle 2, But because angle 1 together is going to be equal in measure to angle 5 and 6 together, that means that angle 1, angle 2, angle 5, and angle 6 are all going to be the same measure. Angle 1 will be congruent to angle 2. Angle 2 will be congruent to angle 5. And angle 5 will be congruent to angle 6. All 4 of those angles will be congruent. That is not only because of this theorem 6-14, but also because of our properties from parallelograms. And of course, that same logic goes for angles 3, 4, 7, and 8. Angle 3 will be congruent to angle 4. Angle 4 is going to be congruent to angle 7. And angle 7 is congruent to angle 8. All 4 of those angles will be congruent to each other because of the combination of theorems. This theorem about rhombuses, the diagonals are bisectors, and because of our properties of parallelograms. Okay? Questions on that theorem? Okay. One more thing I would like to talk about then. Because second semester we are now getting into a lot of geometry that is pulling from things we talked about in first semester. Okay? In my opinion, this is when it starts to get interesting. Because we're not just learning one little thing here, one little thing there, all separately. We're now putting stuff together. Things are starting to basically come together and be relatable to each other. Okay? So the nice thing here is if you forget properties of rhombuses, if you remember previous properties we talked about, you can recreate it. Okay? You don't need to know all the details if you remember some of the big picture stuff. You can recreate the details. Okay, so I apologize, folks watching the video. I forgot to push record here, but we just talked about there in blue that diagonal AC is cutting that into 2 isosceles triangles, and therefore by side-side-side congruence of triangles, we can show that our 4 angles are congruent. And because rhombuses are parallelograms, we know the opposite angles are congruent. And again, because of definition of isosceles triangles, we know that base angles are congruent. So all those properties together come and tell us that, hey, those 4 angles are all congruent. Just like we said earlier in the theorem, 6-14. But now we want to talk about line segment BD, which is the other diagonal. And the theorem I'm trying to show now is the first one there, 6-13, that the diagonals are perpendicular to each other. Now, that comes into play in the fact that if we look at just one of the triangles, such as the top one, if we look at one of these triangles, like this guy up here, and if we then say, all right, we already know theorem 6-14 that the diagonals are angle bisectors in a rhombus, that means that we know that this angle is congruent to this angle. Okay? So going back to a theorem that we talked about in Unit 2, Chapter 4, dealing with isosceles triangles, if a segment drawn from a vertex is an angle bisector, then it must also be a median and an altitude. So we know that this segment has to be congruent to this segment, which is fine because that's actually one of the properties of a parallelogram. A property of a parallelogram says the diagonals bisect each other. Cool, another detail, connecting the dots. It's a median and it's perpendicular. It's an altitude. Okay, and that's where then the theorem for rhombuses come into play, in that the diagonals are perpendicular to each other. Okay? So all of these properties come together, folks. All of these things we've been talking about for months now are going to start coming together here in the last half of the school year, or almost last quarter of the school year. Okay, So before we move on to the back side, let's go ahead and look at a couple of examples of where all these things work for us. So in our first example on the page, we want to find 4 missing angles. I'll give everybody a moment to come up with a strategy. Ready, set, go. So taking a look at this, anybody have a good reason for finding any particular angle to start with? Yes, ma'am. Angle 3 and 2 are congruent because we have that property 614? Yep, 614 says that the diagonal BD must be an angle bisector, so we know that angle 3 and angle 2 are congruent. That is an excellent thing to know. Sadly, right now, that doesn't tell me what the measures are. So what else might you do?
Well, angle 3 and angle 2 are 58 degrees because angle ABD is congruent to angle 2 and 3.
All right. We can say for, again, multiple reasons. Multiple reasons. Remember that we have a rhombus. They tell us it's a rhombus. And so you could have said, well, I have congruent sides here, making triangle ABD an isosceles triangle, and therefore angle 3 is a base angle congruent to the other base angle, 58 degrees. Perfect. That would have been beautiful. Or we could say, well, wait a minute, a rhombus is a parallelogram, and therefore its opposite sides are parallel, making the 58 degree angle and angle 2 alternate interior angles. So again, angle 2 is 58 degrees. Awesome. Okay? You could have gone a longer route and said, all right, well, if the diagonal is an angle bisector, then that makes this 58 degrees as well. And I know that the opposite side or opposite angles in a parallelogram are congruent, so therefore angle 2 and angle 3 together must add up to 116 degrees. And then, well, wait a minute, we have an angle bisector, so cut it in half and we're back to 2 58 degree angles. Okay? But again, folks, you seeing how when we're working these problems now, there's going to be multiple ways of going about it. Multiple different properties are at play. Is any one way right or wrong? No. Is any one way shorter than another? Yeah, maybe. Okay? But there's lots of ways to getting to our answer. So, all that being said, we have now said that the measure of angle 2 is 58 degrees. The measure of angle 3 is 58 degrees. We still need to find the measure of angle 1 and the measure of angle 4. Any ideas? Yes, ma'am. Yes, Jessica.
Add the angle B, and then add, well, half.
So you're saying angle ABC, that whole thing?
No, ABD.
ABD, so 58 degrees, yep.
And then angle 3.
Mm-hmm.
And then subtract it from 180, and then divide by 2.
Okay, so you're saying that this angle plus angle 3 plus this entire angle over here, angle BAD, have to add up to 180 because we're dealing with that triangle ABD. Great. And then this diagonal is cutting that angle in half, so you take half of that to give you your final angle for angle 4. That's a great way of doing it. That would work.
Wait,
Uh-huh.
don't 4 and 3 just add up to 180?
Angle 4 and angle 3 alone? Absolutely not, because 3 angles have to add up to 180 for a triangle, right?
But I thought since it was
No, I know what you're saying. You're talking about being a parallelogram and having consecutive angles be supplementary. You're right, except that would be this entire angle here and this entire angle there. Okay? In which case, you could still do that because we know 2 and 3. Right, so you'd have to use that whole 116 degree angle, okay? And then angle 4 and whatever that other angle is, there you have to be congruent as well. So you could go that route, but you have to make sure you're not just using 3 and 4.
Yeah.
Yeah, it's not just 3 and 4, it's the bigger angles. Okay? Then, so talked about a couple different ways. All right. One thing that I'm seeing real quick that nobody has mentioned yet is angle 1. That's what you were going to say?
Yeah.
Okay, well, what do we know about angle 1? It's a right angle. Angle 1 is a right angle because the diagonals of a rhombus are perpendicular to each other. So, if you know that, and we know angle 3, then we can find angle 4 directly without having to divide by 2 and do all that kind of stuff, because now we can use this small triangle here, where we have a 90-degree angle, a 58-degree angle, and then whatever angle 4 is. So, to find angle 4, we take 180 minus 90, which is 90, and then take 90 minus 58, which is a 32-degree angle. So, is there only one way to do this problem? Absolutely not. Okay, absolutely not. Think through what you're doing. Make sure you're working the whatever properties you want to use, make sure you're working them properly, and they should get you there. Okay? Questions on our first example? None yet. All right, let's go to the second example on the front page. Looking at those angles, what can you tell me about angles 1, 2, 3, and 4? All 4 angles have to be congruent, right? Because the opposite angles of a parallelogram are congruent, and because that diagonal PR is going to be bisecting those. Okay? So we got to know how to find one of them. Because that's what we really need to do now. We got to just find one of them. So, which ones do you want to find?
1, 3, 2.
You want to find 2? We could find 2. It's a little bit more complex than maybe finding something else.
1.
Because 1, yeah, okay, let's find 1. There we go, there you're thinking. Because we can look at that triangle QPR. What do we know about triangle QPR, other than that we have angles 1, 3, and 104 degrees in it? It's isosceles. Why is it isosceles? Because we're dealing with a rhombus. So these sides are congruent. And if it's an isosceles triangle, then we know that angle 1 is congruent to angle 3, like we already said. And so then how do we find those angles?
Subtract 104.
Take 180 minus 104, it gives me 76, and then divide that in half. Okay, 76 cut in half is what? 38. So therefore, we know the measure of angle 1 is going to equal the measure of angle 2, is going to equal the measure of angle 3, which is going to equal the measure of angle 4, which is going to equal 38 degrees. Now, could you have just listed those all out separately? Absolutely. Okay. Questions on our 2 examples on the front page? Go to the back page. We have one property to talk about in a rectangle. And that property for a rectangle is that its diagonals are congruent. The diagonals of a rectangle are congruent. Okay? How do I know that's true? Well, because a rectangle is a parallelogram, therefore its opposite sides are congruent, right? So I know that AB is congruent to line segment DC. And line segment BC is the same length as itself, I'm going to say. I know that I have a 90-degree angle here and there. So I want to look at a couple of triangles. Triangle ABC and triangle DCB. I'm looking at those 2 triangles because I know that they are congruent to each other by side angle side. And I know that they hold my diagonals that I'm talking about. Okay? Those 2 triangles are congruent by side angle side, making my 2 hypotenuses, the diagonals, congruent because they're corresponding parts of congruent triangles. That's essentially how we would prove this theorem. We know the diagonals of a rectangle are congruent because we can show we have congruent triangles. Okay? So looking quickly at the example right next to it, if we are given this information, and pay close attention to what information that is. We are given that SF is 2x plus 15. Well, where the heck is SF? It's a diagonal. Okay? And RB is another diagonal. And we know that we are given a rectangle. So therefore, what's true about our diagonals? They are congruent, or their lengths, SF, is going to equal the length RB. So 2x plus 15 equals 5x minus 12. Let's see, adding 12 to both sides gives me 27. Subtracting 2x from both sides gives me 3x. Dividing by 3, x must equal 9. But is that what they asked me to do? No. They said find the length of a diagonal. So how the heck am I going to do that? Plug it in. Take the value of x we just found and plug it into one of those expressions. So, SF equals 2 times 9 plus 15. 18 plus 15 gives us what? 33. Questions? Now, somebody might ask, well, I didn't want to plug into SF. I plugged into RB. Does that matter? No. Why not? Because the diagonals are congruent. They're the same length. Okay? All right, one last thing I want to talk about quickly. If you go to your flow chart, on this flow chart here, we've talked about quadrilaterals, parallelograms, rectangles, and rhombuses. We haven't talked about squares yet. We haven't talked about squares because squares are all of these things. A square is a rhombus and a square is a rectangle. So therefore, squares have, what did we say, 13 properties to it? Okay? All the properties of a rhombus, all the properties of a rectangle, all the properties of a parallelogram and a quadrilateral all hold true for squares. Okay? So, in working with this flow chart, if you know that you're working with any one shape, like let's say we know we have a rectangle, then these three definitions or these three properties and anything above it, those 5 from a parallelogram and those 2 from a quadrilateral, all are properties of a rectangle. Make sure you go back and look at the higher ordered shapes when you're looking for properties. Okay?